It's actually literally called a cold finger. And what happens is, what deposits on the cold finger? Well, what deposits? Impurities or your substance? Impurities or your substance? What deposits? Yeah, usually impurities. It could be either one. Well, solid, no kidding, Miss Elena, but which one is the solid? Is the solid your impurity or what you're trying to get to? Which one? Which way to go? Got it? Okay. So what we have here is your impurities can collect here, or your unknown can. So generally speaking, it's your unknown that deposit and your impurities stay behind. So what this implies is you have at least an idea of what your impurities are. So you pull your cold finger out, and the cold finger has all these spectacles on it. Remember? And you shave them off. Don't you guys remember doing this? And then you weigh it out, and you're like, oh my God, my yield is like 2%. No one? All right, so long story short, what are we doing it? We're doing it based on when this stuff precipitates out. So different things precipitate out at different temperatures. And as long as that's true, which it is, then we can control the different temperature at which you precipitate. And then the cold finger will precipitate your, hopefully, what you're looking for. So we have A, it precipitates, you leave behind your impurities. I will leave you behind impurities. And we managed to isolate A. And not only did we separate it, but we identified it. Got it? I like it. So that's what the cold finger does. That's my story. I'm sticking with it. Let's move on from there. Let's do extraction. Extraction is a very interesting and cheap way to do things. And you use what's called an extraction funnel. And the extraction funnel has two layers. What are the two layers? Isn't it organic? Don't you think? One layer is organic, one layer is aqueous. What layer is usually on top, organic or aqueous? Organic is usually on top. Do, 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 do. Why is the organic on top usually? Because aqueous has more intermolecular forces. And if you have more intermolecular forces, you have a higher density. And if you have a higher density, you on the bottom. Get it? Good. It's nothing to do with dissolving, dude. It doesn't, yeah, it's really not kind of what we're getting at there. Okay, cool. So you got an organic layer and aqueous layer, and you're right, they don't dissolve with each other. Like doesn't like, so you want them to be organic and aqueous, so you have this barrier. So you drop in your substance A, and you can figure out whether your substance is aqueous or organic. So this separates very nicely. So this is a very nice separation technique. Doesn't really identify what you have, but it's a really nice separation technique. So would this, so basically we need to know all different molecules on this universe and find out whether they go aqueous or organic in a separation. And are there rules? Yes. Rule one is if you're charged. If you're charged, where are you going? Aqueous or organic? If you're charged, you're going aqueous. Booyah. Rule two, zero dipole. If you have a zero dipole, whoosha, whoosha, whoosha. Somebody said I don't whoosha anymore. I don't agree with that at all. You suck, you suck. So in a zero dipole, what happens? So in a zero dipole, what happens is you have no net dipole, and the molecule is phobic. That's what happens in a zero dipole. So you are going to the organic. And the last rule is a Scott special. Ready? If you have 6 or more carbons, only one functional group. What? If you have 6 or more carbons with just one look is all you need. Ooh, just one functional group. 6 or more carbons, only one functional group. That means the carbons outdo your functional group. And isn't it organic? Don't you think? Get it? That's it. Those are the rules. So now it's time to play extraction. So extraction. extraction occurs as such. So what are we going to do? Let's go with carbon tetrachloride. There's a good one. We can extract that. Let's go with benzoic acid. So they'll do these and they'll write them out so they get double bang for their buck. So you're supposed to know what they look like. Let's go with phenol. Let us go with some benzoate. And let us do some. Oh, I got one. I bet you weren't expecting this. 3-octagon. 3-octanone, which is the old school way to do it. Octane, drop the E and put an on. Now they say octane and then 3-one. 3-1. Yeah, same thing, but different. Guess who's back? Scooter's back. Ooh, acetone builds a bony. No, it doesn't. Acetone. When do you make acetone, folks? When you're starving, Marvin. When you're starving, you make acetone. Why do we make acetone when we're starving? Anybody know? Ketone bodies. Acetone's a ketone body. Acetone tautomerizes. So acetone from CoA can tautomerize. And when it tautomerizes, it makes an enol. When it makes an enol, this can carbon attack and actually add a methyl to it. And you get acetone. Is that crazy? It's crazy loco. More to come in biochem. Get your ass to biochem. You'll understand ketone bodies. All right, let's go. Ketone body. First one, aqueous organic. Carbon tetrachloride. Today be good. Organic. Yes. Zero dipole, baby. You're going organic. Isn't it organic? Benzoic acid. Benzoic acid, though, that's carboxylic acid, guys. Come on. It's a carboxylic acid. Oh, it's a carboxylic acid. Aqueous organic. 6 or more carbons, 1 functional group. Don't fall for it. It's a trick. 6 or more carbons, only 1 functional group. Isn't it organic? Don't you think? Phenol. Should you know what phenol is? Yeah. Is that benzyl alcohol? Yeah, but they don't call it that. Where's it? Now that's an alcohol. So obviously that goes what? It's an alcohol, so it goes where? Obviously it goes, has nothing to do with it. It's going organic, folks. It's going organic. Got it? 66665. It's going organic. And oh my God, Rebecca showed up. Damn it. Extraction. There we go. Put it in the right place. Yes, ma'am. Benzoate. Where's it going? Benzenol. That would have been a cute name. I agree, Miss Julie. Benzenol. I like benzenol. Where you going, benzoate? Miss Danielle forgot the rule 1. Bet your bottom dollar she doesn't know. Rule 1. It's negative. It's an 08. It's only a freaking aqueous. Oh, wait. Why do you guys suck at this? Folks, what the hell? These are easy ass rules. Number 1. Do you see the number 1 there? It's freaking charged. If you got a charge, where are you going? So what did we not know? Did we not know that an 08 is a carboxylate? Or did we not know that, it was like 6 carbons? But this is rule 1, which takes precedence over rule 3. Hence, it's rule 1 and not rule 3. Do we understand that? So let us try it again. Benzoate, aqueous or organic? Aqueous. Oh, I like you guys again. So it's aqueous because, good to know. It's aqueous because it's charged. Follow the rules. What are the rules? Octane 3-on. That's probably like a bunch of them, but whatever. Octane 3-on. Organic, that was an easy one. No one's allowed to miss that. 6 or more carbons, only 100. Acetone, okay, pause. What the hell, man? Acetone has 3 carbons, not 6 or more. So you got to extrapolate a little bit. So acetone, big ass dipole here, negatives, positives. So what do you want to tell me? Oh, what do you want to tell me? You're going aqueous, baby. Sweet. Honestly, there shouldn't be a molecule in the universe. Extraction is good for like 4 out of 5 MCATs have an extraction question. So do you think you should know extraction? Yeah, it's cheap, it's easy. Yeah. There's no tricks. There's no. What are the tricks here? There's no tricks. It is what it is. I don't know what to tell you. All right. Now there is one that's a little tricky, and my Dexter fans, you should know this one. What was rule two? I'm not going back, Rebecca. You should know rule two. Shame on you. Shame on you, Rebecca. What was rule two for Rebecca? Of course, I'm going to go back for Rebecca. You guys know I love Rebecca. What was rule two? Zero dipole. Zero dipole. Zero dipole. Come on. Okay. This molecule, you might think, is, well, let me just tell you what happens. This is chloroform. You're supposed to know chloroform. And you're supposed to know chloroform. What happens is these chlorines just push this little hydrogen. He's like, oh, get out of the way. Get out of the way. So you almost take on a trigonal, like a trigonal planar molecule. You understand? So based on me telling you that and making a special point of it, what do you think chloroform is? Phobic or philic? Organic is phobic. Organic. Yep. Good, good, good. This is a classic phobic solvent. Should you know it? Yeah, it's called chloroform. Yeah, yeah, yeah. All right, cool. Extraction. Nailed it. In extraction, oh, Carly, I wait for no one. In extraction, what do you want? Come on, Carly, ask the question. Wait, why is it organic? Dude, where the hell you been for the last like 4 minutes of our life? The chlorines, oh, they push out. Remember, hydrogen is kind of tiny, so really it looks more like this. Chlorine, 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 get your chlorine here. Well, it's nothing to do with a steric thing. Not at all. It's nothing to do with steric. Total lack of steric thing, maybe. So absence of steric thing. So today, Jewel, today's your opposite day. It's absence of sterics. Since there's really no sterics, the chlorines can kind of take the place of the hydrogens, and you get this nice trigonal planar. So if I showed you a molecule like this, it was trigonal planar, and there's a hydrogen, but that's supposed to be three things. If it's trigonal planar and everybody's pulling equally, what would you say it was? Clear as day. What? What? Like BFF? Ah, you guys are my BFF, best friends forever. Forever and ever. So in BFF, phobic or philic? Carly, this is for you. You better pay attention. Phobic or philic? Carly, where the hell are you? We're all waiting on you. Carly, where are you? Hey! Julia says, you suck. What do you mean you don't know, dude? Is there a freaking dipole? Okay, if you had a pole and you tied 3 ropes and you pulled with equal tension, as in fluorine sucks electron density, which way does your pole move? Which way does your pole move? Come on, sister. Which way? No way. No, down? Dude, what the hell does that even move? What the hell? What? Wait, what? You've never tied 3 ropes to a pole? What the hell? No, I'm not moving on, Carly. No, tough shit. You're going to learn this, or else everybody's going to suffer for it. Look, let's say you had a pole and you tied a rope in 4 different areas and you pulled with equal tensions. Is this pole going to move, yes or no? Yes or no? Not no. Hell no. So now, let's go back to our 360 degrees, 120 degrees around. If you had a pole like this and you pulled with equal tensions, do you think that pole moves? This is what we're talking about. This is what a dipole is. That's the whole point. So where is most of the electron density on which fluorine? Well, they're all equal. So that is a 0 dipole. Only if its trigonal planar is correct, but that's what I'm trying to show you is chloroform is like its trigonal planar because hydrogen is such a wuss. Get the idea? So long story short, BFF sure as hell is phobic or philic. I love when you guys open up the can of worms, but then you're like, oh, just move on. I don't want to know it. I don't want to go to medical school. The hell with that shit. It's too hard, man. Get out of here. Come on. Good. 0 dipole. Chloroform is kind of an exception because you might think there's a dipole, but the hydrogen has, according to Joule, the hydrogen has kind of no steric hindrance, which is true. So the chlorines kind of occupy that space. So you were correct to say it's about sterics, but it's literally about lack of sterics because really hydrogen, so it's almost like the hydrogen doesn't exist. The chlorines can spread out in almost a what configuration, folks? In chloroform, in CCl3, in almost a trigonal planar configuration. And since that's the case, would this thing have a dipole? Very, very minimal dipole, almost a 0 dipole. And as such, we get to rule 2, and rule 2 says we are phobic. Everybody understand why chloroform's a section in the class that chlorines are so large. Joel, what are you talking about? That makes no sense and no sense. The chlorines It's because the hydrogen's so small. That's what it is. Yeah. All right, all right, all right. Moving on. Let's talk about another cheapie. Let's go cheap. Distillation. Distillation is by boiling point, but then there's something called vacuum distillation. In vacuum distillation, to understand vacuum distillation, you have to understand what a vacuum is, and you have to understand what boiling point is. So, what boiling point is creating enough energy to break intermolecular forces. So, you need to know the definition of boiling point. So, you're trying to break how many intermolecular forces for boiling point do you break? All intermolecular forces, because you're liberating gases. And that's why the heat of vaporization is always, for all substances, the heat of vaporization is larger than the heat of fusion. Do you know that? You should know that. It's considerably larger. So allegedly, they've asked, why is the heat of vaporization larger than the heat of fusion? Because in the heat of fusion, in the heat of battle here, in the heat of fusion, are you breaking all intermolecular forces? Yes or no? No, 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 no. Because if you were, you'd be a gas. So from solid to gas or solid to liquid right here, we're only breaking the crystalline structure. Then from liquid to gas, we are breaking all intermolecular forces, liberating gas. So that for which substance is it true that the delta H of vaporization is greater than delta H of fusion? Which substance? That's for all substances, folks. And I think I'd want to know that. Okay, so long story short, you got to break your intermolecular forces. Do you boil once you break intermolecular forces? Yes or no? If you broke all intermolecular forces, do you boil? No. Because have you heard a little something called the atmosphere? The atmosphere has its own particles, and you've got to overcome the kinetic energy of the atmosphere. So now I've got to add energy to overcome the atmosphere. So water boils higher in where? Oh yeah, Denver and New York City. Get a root. New York City, get a root. Denver or New York City, where does boil higher? Higher temperature. Which one? Which one? Denver or New York City? So in New York City, because what happens in Denver? In Denver, we're at higher altitude, and higher altitude means what? At high altitude, we have a lower density. And if we have a lower density, there are less particles that we have to overcome. So long story short, listen. Boiling point. So what is 100 degrees anyway? When they quote 100 degrees boiling point, what does that mean? One atmosphere. It means sea level, folks. Sea level. Sea like seal? No, like sea level. You're at sea level or sea line, depending on where you're from. Yeah. Or SEAL Team 6, whatever you want. Got it? So long story short, 100 degrees, we quote, we're at sea level. Is that a thing? Yeah. Is New York at sea level? Pretty much. Is Denver at sea level? No. So what is boiling point? Boiling point is the amount of energy required to break intermolecular forces, then add kinetic energy to the particles to overcome the atmosphere. Then you boil. So if we wiped out the atmosphere like in a vacuum, what happens to the boiling point of your substance? If we wiped out the atmosphere, what happens to the boiling point? Goes down. For which substance? Which substance boil at a less all substances? Yeah. So your boiling point goes down. And is that good or bad? This is good because you want to use it for anything with 150 degree boiling point or higher. Because you don't want to burn up your apparatus. So if something has too high a boiling point, what are we going to use? Vacuum distillation. I feel like that's the thing. All right. While we're on the topic, let's do gas chromatography. Gas chromatography is almost like distillation. So you have a tube, and you have another tube. And then the difference between this and then there's a condensing wire that condenses and cools the gas we're going to make. And inside our tube, so the difference between this and distillation is nobility. We've got a noble gas in here. Oh, sorry, Rebecca. This is gas chromatography. I kind of like it. I like it. So now what happens? Well, we got two unknowns here, A and B. We light them up. So the first thing you have to understand about gas chromatography is it's separating based on boiling points, right? So you should always know what everything separates on. This is based on boiling points. And since it separates based on boiling points, we have a bunch of terms we have to know. Does the noble gas push it through? It just carries it. The noble gas helps carry it down the tube, so it just doesn't conglomerate down here or precipitate or anything like that. So noble gas just helps push it down the tube. Got it? It's like an ebulator kind of thing. So we condense this, blop, blop, fizz, fizz. The one that comes off first, an ebulator is a little thing that blows air across the thing, so you disrupt hydrogen bonds, you don't superheat water. So, you're welcome, Julie. So we cool this down, and the one that comes off first is called what? The one that comes off first, it's most volatile. It's most volatile. And volatile, the one that comes off first is the first elutant. So these are all words you're supposed to be very comfortable with. So the first elutant has the lowest intermolecular forces, has the lowest boiling point, has the most volatility. Got it? Has the lowest flash point, if you will, and you will. So what does a gas chromatography readout look like? Well, there's a 0 point, and there's something called retention time. So if you come off first, tell me about your retention time. Were you retained? You have a very low retention time. So gas chromatography tells you basically what these two things are based on their boiling points for the most part. And it also tells you relative abundance. So we can figure out, so this picture, if this is the 0 point, what do we know about A and B in our solution over here in our starting solution? What do we know about A and B? What do we know about A and B? There's lots of A. Area under the curve is always abundance. Area under the curve is always abundance. I forgot. What's area under the curve? Anybody remember what that is? Abundance. Area under the curve is always abundance. A is more volatile. I agree. A is more volatile, and area under the curve is abundance for all separation techniques. That's the thing, folks, including NMR. The taller the peaks, the more hydrogens there are. So area under the curve is abundance. So let's review gas chromatography. Separates based on boiling point. We have a noble gas to set it into the mobile phase. The noble gas helps move it in the mobile phase. You boil these bad boys, so it implies right out that you have to vaporize your substance. So is this good to separate proteins, yes or no? Gas chromatography. Hell no, you can't vaporize proteins, guys. That's not a thing. So vaporizing proteins is not really a thing. Yes, I'll explain a boiling chip in a minute, Elena. That's like nothing to do with what we're doing, but that's okay. I love random acts of kindness. What does the noble gas help do? It just helps it move. So as soon as you boil it, so here's my gas. It's like, I don't know where I'm going. The noble gas, they like push it through, and it's like, go down there. It's like, oh, okay, I'll go down there. Because it's not really thrilled. That's all. It literally just puts it in the mobile phase. So that's a good question. They can ask it. What's the purpose of the noble gas and gas chromatography? And it's help it to move down the column. So help it to move down the column is the perfect answer. Got it? Who the hell asked that? I think it was Elena. Elena asked about boiling chips. So Elena, don't let me forget that. I'm writing it right here, and I'll still probably forget it. Because you guys should know about boiling chips and emulators. I opened the can of worms, and I'm going to close it. Not like Carly. Yeah, I called you out, Carly. boiling chips and emulator. It's all out of love, girl. You know it. All right. So we got to do that for Elena. Do it for Elena. Here we go. Oh, now. So A and B, what do we got here? We've got A came off first because it's closest to 0. It has the lowest retention time. We should know that B has a higher retention time, and there's less abundance because there's less area under the curve. I don't know. This is pretty much it. Gas chromatography is pretty straightforward, guys. And again, what was the point? Is gas chromatography good for lipids or no? Yes or no? I forget. Good for fatty acids or no? Okay, folks, okay, why are you saying these horrible things? Look at a lot of y'all saying it too. This is terrible. Okay, pause. Fatty acids have what kind of dominant intermolecular forces? What are the dominant intermolecular forces in palmitate, 16:0? What are the dominant intermolecular forces? IDS. Does that mean I don't know, Kenneth? What the hell does that mean? London, there we go. London dispersion forces, van der Waals forces. This is the lowest forces. Do we understand? If it's the lowest intermolecular forces, what do you know about the boiling points? They're low. What does that mean? They're vaporizable. Do we understand? So let's try it again. Is gas chromatography good? Yes or no? Yes. So you know when you go and you get your little, you guys ever hear of a VAP test? Nah, probably not. You get your little VAP test, you get your little omegas. Oh my God, I gotta see how many omega-3s I have and omega-6s I have. You know when you get all that and you drink your omega fatty acid oil, which is just moronic and stupid. But in any case, when you do that and you send it out to the lab, what are they going to do? They're going to do gas chromatography. That's what we do for fatty acids. We analyze them with gas chromatography because it's cheap and easy. Got it? Good. No. Get back in distillation. All right, now let's talk about an nebulator. What's the purpose of a condenser? To cool it down, sister, because it's a gas. We vaporized it, and now we got to cool it down. Oh, by the way, this is always the question, and you should really be very comfortable with this. If you want to increase your resolution of separation, which means how well you separate, what do? You just slow it down. You heat it up and have a longer column. Absolutely correct. Longer time and longer column. Everybody understand that? To increase your resolution, have a longer column and a longer time. It allows for, because if you do it really fast, you may have heated certain molecules and they may come off with the other unknown. Everybody get that? So to have better yield, longer column, longer time. That's a thing. All right, let's talk about boiling chips. You remember you use boiling chips? I always said this was total bullshit, but it's not, because I had a student who actually blew up their Erlenmeyer flask and had to pay $170 from NYU. True story. He's like, no, man, I blew it up. Yeah, true story. I've tried to blow up flasks and couldn't blow them up. But anyway, here you go. Here's what happens. So there's a whole movie based on this with Keanu Reeves. It's like a 1990s stupid ass movie where he is going to save the world's energy problems, because Keanu Reeves plays the role of an astrophysicist, which is very believable, and he's going to save the world from energy because he's going to use superheating of water. No, you didn't, Julia. Did you really shatter an Erlenmeyer flask? Are you telling me the truth? You're my hero if you did. Navy, yeah, you're full of crap. All right, here we go. What happens is this. When you heat water from below, okay, because there's hydrogen bonds up here and there's this surface tension, water doesn't want to leave immediately. And what can happen is, instead of leaving because of this surface tension that's created, you can actually cause the water to bring its heat back down and superheat for just a nanosecond, and that's going to expand and crack the container. So what do you want to do to the surface tension up here? What do you want to do? So you understand, so you're heating it from the bottom, you want to break up the surface tension. So you're heating it up, and you got the surface tension that kind of brings the heat back down, and when it does, you get superheating and the container cracks. And it can actually blow up pretty well. So what do you want to do with your surface tension? Throw in a Berlin chip. So a boiling stick, they have boiling sticks, they have boiling chips, and you also can use an ebulator. So an ebulator, picture like this, here you are, blowing some air. Got it? So you're blowing some air across. So an ebulator blows air across. So what's the purpose of an ebulator? What's the purpose of an air? It doesn't make higher intermolecular forces with the surface. It doesn't. No, there's a surface tension. Water has a surface tension because it binds, doesn't want to bind with the air. The purpose of an ebulator is to disrupt the surface tension. What's the purpose of a boiling chip? Say the same thing. Purpose of the boiling chip is to disrupt the surface tension. Do we understand that? You should really understand that. Everybody get it? Purpose of a boiling chip and a purpose of an ebulator is to disrupt the surface tension. And that surface tension, like I said, can heat up so hard you get superheating in the water. So you want to prevent superheating. Got it? Elena, did that good explanation? I think so. One for Scott points. Elena, did you say ebulator blows air? I did say an ebulator blows air. Your horn blows. How about your ebulator? Yeah, your ebulator blows air. Got it? And it makes bubbles, yes. And what do the bubbles do? The bubbles disrupt surface tension and thereby prevent superheating of water. Is that really a thing? Yes, because apparently other people have done it. All right, that's my ebulator story. That was kind of tied. It was kind of related, so much props to you guys. Let's do some funner things. Let's do some UV. What does UV do? How do boiling chips? They just don't allow surface. If you have a boiling chip in here and it's floating around, it's not going to allow water to hydrogen bond with itself. Got it? UV light is not, you're thinking of infrared, dude. Infrared is vibrations. UV is about what? So if you absorb UV light, so UV light is an identification technique. Got it? UV light is an identification technique. And you're trying to identify conjugated systems. So UV light identifies conjugated systems. What's conjugated? Alternating double bonds. It's like nauseating hearing that. What's a conjugated system? Alternating double bonds. No, conjugated is greater than 2 sp2. If you have more than 2 sp2s, what are you? Greater than 2. 2 is greater than sp2? That makes no sense. If you have more than 2 sp2s, what are you? You're conjugated. Greater than 2 sp2. How many sp2s do you need? 2. No, you need greater than 2. Yeah, greater than 2. Greater than 2 sp2, you're conjugated and you'll absorb UV light. The more conjugated you are, the more UV light you absorb. So let's play. Ready to play? I knew you guys would come here for a reason. Let's play. Which one of the following has the highest UV absorption? Which way is my UV absorption go? Do 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 do. So far, so close, but yet so far. Macedonia. So it's okay. All right, so let's talk about what you're trying to do. Conjugation is delocalizing p electrons. So if you can spread out p electrons, you're more conjugated. Got it? So which one of these spreads out the most p electrons? Spread them out, baby. Who spreads them out the best? You're the best. No, you're the best. I'll give you letters because you guys, for some reason, don't like to answer without letters. So I will give you some plum colored letters. So how's the question go? The question goes rank order based on UV absorption. Clear? Do it. Who's number one? Who's number one? Who's number one? Oh man. D's number one. D's number one. 2, 4, 6 p electrons delocalized across 6 bonds. And that means what? Does that have meaning to you or no? Should have meaning to you. I feel like it does. Well. Fully conjugated. Absolutely. D is fully conjugated. As a matter of fact, it's aromatic too. The next one, Ian's looking pretty good there. Look at this. I got 2 electrons and I'm going to distribute across 6 bonds. I agree. D is going to have more UV absorption than A. Who else? How about C? Why'd you take A over C? Why not F? Why not 2? Why not 3? What about F? What about us? What about all the times we're down? What do you got? There we go. F is fewer molecules but more electrons to delocalize. So what do you think is more important, spreading out electrons or not? So this is a PPP. Yeah, you want to spread out more electrons. The more electrons you can spread out is better. So what do you guys think? Spread them, baby. Who's next? Give me a letter. Give me a head of hair. Shoulder length longer. I agree, F. Yeah. Why aren't A and D equal? Why aren't A and D equal? Seriously, dude? There's 2, 4, 6 electrons. There's 6 p electrons here. Here, there's only 4 p electrons. So you're delocalizing more p electrons. The universe likes you when you delocalize more p electrons. That means you're more conjugated. Got it? Oh, and then that's when you say, oh. So now, that's why F is better than who? Who's next? So D and F. Let's get rid of 2 right away. B has no conjugation. E has no conjugation. Do we agree? I'm so glad we had this time. So now we're down to A and C. Who's next? E has no conjugations. It's gone. It's useless. What do you got? I agree. So we have 4 electrons distributed across 1, 2, 3, 4, 5, and 4 electrons distributed across 6. I'm taking E, D, F, A, C, and then the B and E. are useless to me. Nice. UV absorption, do it by conjugation. We'll all get along just fine. All right, let's do IR. IR is so much fun. IR is the one that senses vibrations, and it's good for functional groups. It's really not good for a lot of functional groups. The only functional groups they've tested with IR are two. For functional groups for IR, we need to know an OH, and we need to know a Q, and we need to know a carbonyl. Sure, Julia, sure. So to go back this way, which we are going to, good. So now let's do IR. So what do we need to know? We need to know an OH, regardless of where it's coming from, is what's called broad. And it's broad between 2,900 and 3,600. Then we need to know a carbonyl is sharp, and sharp means the opposite of broad. And that's between 1,700 and 1,750. Aight. So if that's true, which, you know what? It is.
Hi, sweetie.
Let's take a look at that.
Love you. Hope you're having fun.
0 can be on either side, folks. And the humps can be up or down. So if 0 is here, and this is here, and this is here, what have you got? What have you got? Bloomin' what have you got? What the hell have you gotten yourself into? What do you got? Can anybody tell me what the hell you got? Oh, you need to label it. You need to label it. All right. Hopefully you realize the point we're trying to get at here. 17 to 70, 50, and 29 to what? About 3,600 somewhere. Okay, how's that? Yeah, probably have a carboxylic acid. Can you tell really? Not really. You can't tell if it's a carbonyl with an OH, but this is probably a carboxylic acid. But sure as hell you have an OH somewhere, and sure as hell you have a carbonyl. And that's pretty much what infrared is good for. Besides that, it's utterly useless. Got it? Good. All right, moving on. That was fun. So much fun. Let's do some bead stuff. Now let's do some TLC. We didn't do any TLC yet. TLC. Thin layer chromatography. So TLC, thin layer chromatography, how does that work? Yeah, we all need some TLC. So in thin layer chromatography, there's something called an RF value. This is really cheap too, and this is very commonly tested. And the RF value is the distance your unknown travels. For IR is abundance area under the curve. No, for IR abundance is not area under the curve. So yeah, that is an exception. Thanks, Rebecca. Thanks for spoiling my mojo. Distance of the unknown over distance, but that's a good question, of the solvent front. Got it? Distance of the unknown over distance of the solvent front. Now, if your RF is big, are you phobic or philic? If you have a really big RF, you are it depends. It depends on the solvent. Good. Don't fall for that. Depends on the solvent. So if I stick you in some benzene, am I allowed to do that? Well, I don't suggest you do. It's a carcinogen, give you mutated babies, so that might not be the best. But if I so decide to put you in some benzene, if I put you in some benzene, love me some benzene. Good job, Ian. And let's say you did that. What do you have with benzene? What do I expect you to do in acetone? What are you going to do in acetone? Your RF should be what in acetone? What should your RF be? Very little. Not the same. What? Olena, what? What the hell? If you move in benzene, you're phobic. Acetone is philic. Remember, it's only 3 carbons, 1 functional group, big dipole, minus positive, remember? So acetone is a philic solvent. So I expect you to do what? Boop. Boop. You're not going to travel much. Capillary action, solvent moves, where'd you go? Boop. Everyone understands. So then they'll give you a bunch of molecules and be like, oh, is my unknown this? Is my unknown woozy. This is my unknown woozy. This. Get the idea? Letter, sorry. Heaven forbid. A, B, or C, which my unknown? Somebody tell me what the heck my unknown is. Charlie. It's definitely not going to be Charlie. Look at the negative sign. It's not Charlie because that likes acetone because it's negative. It's only a Bravo away. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, no, no. No, no, no. No, 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 no. This is noninforon. Noninforon. And noninforon is a phobic molecule and will travel better in benzene than sure as hell will, whatever hell this is, octanoate or heptanoate. O8s are negative. They will be philic. Got it. I wonder if you all know. So TLC, you got to know the solvent. Got it. So the RF is literally, you look up RF depending on solvents, but it's really cheap to pour out a bunch of solvents, dot your unknown on a piece of paper, and just run it. There is one special TLC paper called what? Silica. And this violates all rules. The silica paper itself, the silica paper is philic. So it's like a glue trap. The silica paper is philic, so it traps philic things. So regardless of the solvent, it doesn't matter. So if you have a large RF, please know this because I test silica a lot because it's very commonly used. If you have and I promise you, if you only use silica in undergrad, it's not the only TLC out there. So don't believe everything you think you know. So if you have a very large RF on silica paper, what does that mean about you? Now you can tell me. No. Yeah, a lot of people are putting out. Yeah. I'm getting half and half, and this is depressing me. Listen, the paper holds you in the stationary phase. The paper holds you in the stationary phase. Philic sticks to the paper. So if you're moving, what's going to happen? You got it, Miss Sydney. You're phobic. I agree completely. Got it? So what if the solvent's blah, blah, blah? Doesn't matter what the solvent is. If you have a high RF on silica paper, phobic, period. Exclamation point. Write it down. Get this down because a lot of you didn't know this for some peculiar reason. Get it? I like it. Let's focus here. You guys got to focus. Get it? Isoelectric focusing. You guys got to focus. Isoelectric focusing. So normally you have a high RF. There's no normally, dude. It depends on if it's silica paper or not. No, there's nothing to do with it. What do you mean? It totally depends on the solvent for most TLCs. Got it? Let's do some isoelectric focusing because this is fun. You ready to have some real fun? So here we have a gel. And this is a cute way they tested this. What's it called? What's that W mean? What's a W? Why didn't it move a lot in acetone? Because over here, you mean this guy? Colin's like 7 slides behind. If you moved in benzene, dude, you were phobic. So look, this line, you're supposed to know that line is a solvent front. So the solvent moved, and you moved a shit ton with the line. You see what I'm saying? So if you moved in benzene, that means you're a phobic molecule. I wouldn't expect you to move in a philic solvent, and you don't. Colin, you good? It's all about you, Colin. Got it. Good. All right, now back to, you're welcome. Isoelectric focusing. What's the W mean? W. Well. Yeah, it's where you loaded it. And you can have the well on the top or bottom. It doesn't matter. It's because you know what? It's not top or bottom. This is a picture of a damn well. You understand? This is a picture of a gel. It's not even real, guys. I hate to tell you. Okay, so now what happens in isoelectric focusing is on this gel, we set up a pH gradient. And we go like from pH 14 ... all the way down to pH 1. And I forget, is the top the anode or cathode? Anybody know? Does it matter? Yeah, if you want to go to medical school, it matters. So is the top the anode or cathode? Anybody know? Because I can tell you, the top you think is the cathode, huh? You don't say. Top's anode or cathode? I got anode, I got cathode, I'm getting anode, cathode, anode, cathode, anode, cathode. I agree it's one or the other. Okay, let's try this. The first thing is I loaded you in a pH of 14. So what functional groups are deprotonated out of the pH 14? All of them, all your functional groups, all your Cus and your ammonias. And if a Cu is deprotonated, it's a minus. And if an NH3 is deprotonated, it's an NH2. Yeah? So what's your charge on your protein or on your amino acid? Because this is good for proteins and amino acids both. What's your charge guaranteed on any protein amino acid at pH 47? 14, 47, 14 too. You're negative. You're negative. You're negative. You're deprotonated. You're deprotonated. You're deprotonated everywhere. pH 14, you're negative. pH 14, pH of 1, you're positive. Because you have protons everywhere. Protons everywhere. Protons in your hair. Everybody's protonated. So the Qs are like this, and the NH3s are protonated to be 4 bonds. So let's try this again. pH of 14, what's your charge? You're negative. So to set you in motion, to put you in the mobile phase, I better have a negative or positive charge up here. At the top. Negative or positive charge. Okay, so let's try this again. Why are we going so slow with this? If I put you in a pH of 14, you're deprotonated and you're negative with 100% certainty. So to set you in motion, I better have a negative charge. So a negative charge makes you move. Get it? So the negative, how's that work? The negative is the what? The negative is the canode. I'm not getting that. The negative is the cathode, folks. The negative is the cathode. You've been scammed. The negative is the cathode. You're thinking of galvanic cells and GChem batteries. For electrolytic batteries and electrophoresis and anything to do with isoelectric focusing, it's always the cathode's negative. That's the thing. Got it? Cathode's negative in electrophoresis and electrolytic batteries. You're thinking of galvanic, which we're not doing right now. Cathode is positive. Got it? So in electrophoresis and electrolytic batteries, cathode is negative. So you're negative, this is the cathode. So how did they test this question? They did it just like this. And they said, hey, is pH of 14 up here? Is that the cathode or anode? You were expected to know that the molecule was negative. And you were expected to know this would have been negative, pushing it in motion, booyah. When does it stop? When's the molecule stop? At a pH of what? At what pH does the molecule stop moving? I like to move it. A pKa is a function group. It's not an overall molecule. What's the pKa? When you sum all your pKa's, you get a what? You stop at your pi, folks. Your isoelectric point. Your isoelectric point is the pH where you're a what? A Zwitter ion. Your charge is 0. Yeah. So what pH is that? It's all different. That's the whole point. Every protein has a different pi. So this is a really nice technique for proteins and amino acids. And this is what we do to separate amino acids every day in every way. Got it? Good. Okay, isoelectric focusing. I wonder if you all get what a zwitterion is. Oh, I get it, Scott Roberts. I'll tell you right now. You want to know what a zwitterion is? I'll show you a zwitter. So let's explore that for a moment. For one moment in time, let's explore the thing known as a Zwitter ion. Because I think you're all mighty suspect. So the Zwitter ion, what's the charge on the Zwitter ion? So is this a Zwitter? Is this a Zwitter right here? So this is 1, 2, 3. You should know this is glutamate, right? Glutamate. Is that a Zwitter ion? No. Nah. Why not? It's neutral. Don't tell me Zwitter ion is neutral. That's not a Zwitter. Oh, you need charges on it. My bad. Okay, gosh. My mistake. You need charges on it. Now I got it. So this is a Zwitter, right? That's a Zwitter. You guys are quiet. I like it. Mo. Jake, Mo is not an answer. You're mooing, Jake. What the hell does that mean? Is this a Zwitter, yes or no? No. No. Looks like a Zwitter, talks like a Zwitter, but it's not a Zwitter. And Elena, you mean no. Ms. Rebecca, you mean no, it's not a Zwitter. At what pH? A Zwitter ion, okay, so let's step back. Howard, you've only protonated 1 Ku. That's the whole point. Well, you can, and we'll get to that in a minute. So a Zwitter ion is the most abundant ion, nay, is the only ion present at the pi. Only ion present at the pi. So it has to be a majority molecule. Is this ever a majority molecule? Well, I would hope that you know the pKa of the amino terminus is 9, the pKa of the carboxy is 2, and the pKa of this guy's about 4. Which means lowest pKa means highest Ka means strongest acid, means this guy should have got deprotonated first. So I'm going to ask you a question that's going to hurt your brain a little bit, so pay attention because it's a little bit confusing. Listen, at what pH does this molecule exist? And by never, you mean all. This molecule exists at all pHs, folks. All. There will always be some of this molecule. At what pH will this be the majority molecule? Now you can go never. And that's why it's not a Zwitter, folks. This is not the Zwitter. So this is not a Zwitter because it's not going to be the molecule at the pH. It's never going to be the most abundant. But this molecule exists at all, and you need to understand that. And we're gonna come back to this right now. And so I guess we never left it. So listen, let's learn. What did I do? Let's do this guy. We'll do the same one. So I told you, at what pH does this molecule exist again? I forgot. Oh. But now let's just do something totally ridiculous. This is crazy. Crazy. At what pH does this molecule exist? Say it again, same thing. You can keep saying it because it's going to be right the whole time. All. And this molecule, wait, the ammonia lost its proton? The answer is all. Do you understand? So now let's understand this. If you are at a pH of 7, does this molecule exist at a pH of 7? Yes or no? Yes. All. Danielle's like, 7? That's not a part of all. I never include all of my 7s. Danielle, your finger slipper. Good. So, at pH of 7, does this molecule exist? Yes or no? Hell yeah, it does. Now listen, let's have some fun. No, listen, Kenneth, you're being myopic. You're thinking too myopic. You're thinking about one molecule and not understand really what's going on. Everything is about ratios. So listen, at a pH of 7, this molecule should still be protonated, right? And most of them are. So the amino terminus, how many would be deprotonated? If its pKa is 9, that means that 1 out of 100 exists like this. Do you understand? When you are in a pH below your pKa, you're protonated 100 to 1. So at a pH of 7, the amino terminus has 100. They asked this allegedly on the January test, and this is exactly how they asked it. So y'all better pay attention to get this right, because this isn't that hard, and it's showing that you're being too myopic and thinking about there's only one molecule in solution. There's always thousands and millions of molecules in solution, moles and moles, oh my. So at a pH of 7, do you agree that you will have some deprotonated ammonia? Yes or no? Yes, you'll have 1 in 100. 1 in 100 will be deprotonated. Now, most of the molecules at 7 should be what for the R group? They should be deprotonated. So the pKa of this bad boy is 4, and that's something you should know. The pKa of the R group on aspartic acid, glutamic acid is right around 4. So if that's the case, how many R groups will be protonated? Protonated, not deprotonated. Deprotonated should be 1 over Yeah, do you guys get this? So your ratio, guys, no, wait a second. This is threefold difference between your pKa, which means the exponent is 3. So the ratio is 1 in 1,000. Who's the 1,000? This is the Henderson-Hasselbalch, guys. This is what this is, but I'm doing it in an intelligent manner. Okay, no. Amino, Julie, we left that about 7 minutes ago. Listen. Okay, listen. Oh my God. No. Okay, listen. Okay, Do you see that? We're doing the R group. Everybody pay attention. We're doing the R group. Look, Julia, it says R group. That R group at a pH of 7, does it ever exist protonated, yes or no? Yes. Okay. There are two forms of this R group. There's a COO minus form and a COOH form. When is the COO minus the COH 1-to-1? At what pH is it 1-to-1, folks? pH of 4, the pKa. You understand? So it's 1-to-1 at the pKa. At a pH of 5, who's more? The COO minus or the COH? CO minus by 10-to-1. At a pH of 6, who's more? 100-to-1. At a pH of 7, who's more? 1,000-to-1. Do you understand? So if you have 1,000 of these guys, 999 are CO minus. What's the other one? The COOH. So what's the probability of seeing a protonated, listen to the question and please write it down. What's the probability of seeing a protonated R group at a pH of 7 for glutamate? 1 in 1,000. Yeah, you're not gonna do 1,001. Yeah, it's really 1,001, but you're gonna write 1/1,000. 1/1,000. Okay, so now let's bring it home. Listen. The carboxy terminus should be in the form COO minus. But now for 1-to-1, we go back down to 2. So how many zeros is this now? 5 zeros. Do we understand? 5 zeros. So if it were 3, so if it were 2, pH of 2, the ratio of COO minus to COH is 1-to-1. Then it's 10-to-1. Then it's 100-to-1, 1,000-to-1, So this is 1 over, so it's 10 to the minus 5. 1 over 100,000 possibilities. So for every 100,000 molecules, you will find a protonated carboxy terminus. You want 3 independent events to occur. So I asked you, you're digging into the bowl of marbles, you understand? And you're trying to pick out, at a pH of 7, you're picking out one of these. Is it possible? Well, yeah, it's possible, and a lot more possible than you think. Because I'm going to show you. So the answer is 10 to the minus 5 times 10 to the minus 3 times 10 to the minus 2, right? So it's 10 to the minus 10. So it's 1 in 10 billion. There's a 1 in 10 billion chance that you'll find this guy. 1 over 10 to the 10. Everybody see that? Let's see. 5 and 3 is 8 plus 2 is 10. So 1 over 10. But now listen, that seems obscene and it seems a lot. But I'll tell you why it's not that much. Is a mole a whole lot? Like, can you have a mole of alanine, a mole of aspartic acid? Is that like possible, or are you going to like fill the entire Earth? No, a mole is nothing, guys. You know what a mole is. A mole is it's one AMU. It's the molecular weight, so it's not that many grams. It'll fit on a teaspoon. In a mole, there's 6 times 10 to the 23rd. So listen to this. If you had, yeah, we're going to do another one in a sec. If you had 1 billionth of the molecules, how many molecules would exist like this? 6 times 10 to the 13 molecules exist out of that mole. Do you understand what I'm saying? So think about that. It's a whole big of a number. And so there's still a shit ton of them floating around. Does everybody understand that? But relative to the amount you have, it's minuscule. All right, we're going to do one more just because we can. Let's stick with lysine, because I like lysine. I likes you, lysine. Now listen, look. And we're going to do the same thing with the Zwitter, because you guys were like hell-bent on Zwitter being something it wasn't. So for lysine, let's do this. Okay. Zwitter, yes, Zwitter, no, Zwitter, hell if I know. All you is what's up. You should know 2, 9, and 11. You should know these numbers for lysine. If you don't, get to my biological molecules class. So, are you lysine? Is this the Zwitter of lysine? Is this the molecule at the PI, yes or no? Okay, question. Who was the stronger acid? Was the ammonium in the ammonium terminus or the ammonia in the R group? Which one was a stronger acid? Okay, y'all got to get a lot better at this, right? So the lower the pKa, the higher the Ka, the stronger acid. Do we understand? So who's supposed to get deprotonated first? The amino terminus or the R group? So let's the amino terminus. Is this a zwitterion? Is this lysine zwitterion? No, it should be the other way around. It should be COO minus, NH2 neutral, and NH plus top. Do you understand? So listen, let's try it again. At what pH is this the majority molecule? Okay, look, never, 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 never. Because to be a majority molecule, I would have had to deprotonate more of the amino terminus than I would have had the R group. Is everybody here? Now, at what pH does this exist? Oh, I love it. I love it. Now I'm going to ask you, at a pH of 7, you're going to put your hand into the jar of marbles. Here you are. You're going fishing for the jar of marbles. I don't know why you're fishing with your legs, but you're going fishing. That's you fishing. You're going fishing for the jar of marbles. What's the probability you pick this out? What are you going to do? You're going to shoot blanks. And each one of these blanks, small is not the correct answer, Rebecca. So you're going to shoot blanks. And not as small as you might think. Right, Kenneth? The carboxy terminus. What's the probability that you picked out a molecule with, let's do this first, the carboxy. What's the probability that you picked out a COO minus? Who's got it? pH of 7. We're doing pH of 7. All right. Wow, these are terrible answers, guys. Listen, stop. Listen. Okay, listen. No, stop. I can't. No. You're all backwards. The ratio is 1 to 10 to the 5th. Who's the 10 to the 5th? Who's the 10 to the 5th? No, that's not an answer, Dan. Oh my God, guys. The 10 to the 5th is the COO minus. Who's the 1? The COOH. So you have 100,000 molecules. Yes, 10 to the 5th. And 999,000 of them are what? One of them is COOH. 999,000 over 100,000 is the probability that it's COO minus, which is 99.9999. So it's 100%, near 100%, just slightly under. Does everybody understand that? The probability you pick out a molecule with a COO minus is 100%. You guys never saw this in freaking biochemistry. They were supposed to teach this to you because everybody's like, they teach you to be so myopic that there's only one molecule in solution. And what the problem is, molecules like this will still react. They'll be like, how the hell did that react? You would have to have this. Well, that molecule exists. Get it? Okay. Does everybody understand that 99,999 of the molecules are COOH, and only out of the 100,000 molecules, only one of them COOH, the rest are COO minus. So 99.9, so 999,000 are the COO minus over this. This is 1 over 100,000. What are the other 99,999? They're COO minus. So COO minus over total is this. So I'm going to take that as 1 if you guys don't mind. 99.99, I'm taking a 1. Okay, now, at a pH of 7, should you be protonated, yes or no? Is that usually protonated at a pH of 7? Okay, folks, this has got to get better. The pK is 9, you're supposed to memorize it. So the amino terminus pK is 9 for almost all amino acids. A little bit off, maybe 8.8, 9.2, 9.1, but 9. So at a pH of 7, there's more protons than your pK. Your pK is a 1-to-1 ratio, right? So at a pH of 9 for the amino terminus, it goes NH3 plus and NH2 in a ratio of 1-to-1. That's at 9. At 8, you're more acidic, so it's going to be 10-to-1. At 7, you're going to be what? Okay, I need you guys to get on with this, folks, because this is very, very high yield. You're going to be protonated in what ratio at a pH of 7? What ratio will the amino terminus be protonated? 100 to 1. 100 to 1. Okay, so now, Rebecca, pay attention to this so I don't have to teach the other one again. Listen, you've got 100 to 1, and 100 are the positives, and the 1 is the 0. Do we agree? So basically, it's 100 over the total of 101, which we can just call it, 99 to 1 if you want, whatever the case may be. So it's 100 over 101, because, right, 3 boys and a girl were in a room, 2 girls in a room, there's 5 total kids in a room. So there's 101 molecules in the room. Do you get it? One of those will exist in this form, in the neutral form. One of them. Out of how many? Out of 100. What are the other 99 out of 100? One exists in the neutral form. What are the other 99 out of 100? They're the positive. Do we get it? They're the positive. Hallelujah. So if that's the case, the probability for the amino terminus to be positive like this is what? 99%. It's exactly 99%. I'm going to put 1, but it's exactly 99%. I don't care if it's 99% because I know this is not going to be, anywhere near that. It's 99%, guys. Because again, let's try this again. Do you understand that 1 out of 100 will have a 0 charge? 0 out of the positive. If 1 out of 100 are going to have a 0 charge, then what does that mean? No, it shouldn't. So let's go back over to this guy. Okay, if this guy has a pK, at 7, should he be protonated or deprotonated? The R group. Should be protonated or deprotonated? What should be more abundant? We're doing the R group now. The R group should be more protonated. At a pH 11 of 101, a pH of 10 is 10 to 1, pH of 9 is 101, pH of 8 is 1,000, pH of 7 is 10,000. Do we understand? So this should be, how many of this exist at a pH of 7? Most of them should be this. Agreed? Positive. What's the ratio? 1 for every 7 minus 11, 4. 1 for every 10,000. 10,000, not 2,000. It's 4 and 3. So it's 11 and 7. Got it? 4. So the answer to this question, I suggest you review this, guys, because this is probably the only place you're going to see it, because I haven't seen these on any practice tests, unfortunately. But they popped up on this test. So the answer to this question is 1 in every 10,000 molecules you pull out will look just like this. Everybody get it? This is Henderson-Hasselbalch, and this is a major application of Henderson-Hasselbalch. So now we know it, kind of. Good. Yeah, that's great, Rebecca. All right, moving on. We'll talk about it later. Okay, let's do some. That was so exciting. Oh man, you guys killed me. Oh, let's do the ion exchange. Ion exchange is like, I bet like 3 out of 4 MCATs are good for an ion exchange. So ion exchange chromatography is kind of weird, right? It's kind of easy, but it's just, the terminology sucks. So there's cation exchange, and there's anion exchange. If you guys don't get what I just did, get to my biological molecules class when I do titrations and be like, hey, can you do that thing where the thing is like the thing? And I'll do another example. So make sure you ask me. If you get it, I'm happy. But if you don't get it, you better get it. So go talk to somebody. Go seek help immediately. But if you don't get it, get to my biological molecules class, and I'll do it again when we do titrations of the amino acids. Got it? Good. I won't remember. I don't know when the class is. You look it up online. It's on the. I don't know what the hell I'm teaching day to day. I do the same thing you guys do. I look on the website at the calendar, and it's like, oh, that's what I'm teaching today. Got it. And usually I do it right when I'm logging into class. So I have no idea, dude. I don't know when the biological molecules class. Just look online. It's all there. All right. So here, cation and anion exchange. These are two different things. They love this because, and the stupid thing about this is it's a 50-50 chance you get it right. And they've been testing the hell out of it because everybody gets wrong. Because the terminology is honestly stupid. Okay, so now listen. Let's see. Let's see how we do. In cation exchange, what's in the column? Actually, let's do. In cation exchange, what's the elutant? What's the first elutant in cation exchange? Not bad, not bad, not bad. Okay, so here's how it goes. So yeah, so here's the terminology. The cation. So the goal is this. I've got a solution, and they'll ask when would you want to use cation and anion exchange. So it's not bad. Okay. So when would you want to use it? You want to use it when you have molecules that are separated in pretty big charge. Got it? So let's say I have 3 molecules in here, and I know I have 3 molecules, but I want to separate them. So cation exchange is great when you have, if you have 2 positives, it's kind of useless. But if you have a positive, 0, and a negative, it's good. Okay, in cation exchange, the cation exchanges with the negative ions in the tube. So there's negative ions in the tube. So I like that, Mr. Kell, I'm stealing that. The cation exchange catches the cations. I kind of like that. And I've actually never heard of that. The cation exchange catches the cations. Got it? So that's not bad. So in cation exchange, the cation exchanges with the negatives and gets trapped in here. And that means the elutant will be the negative. So she's like, yes, I've influenced Scott Roberts' life in the littlest way. You have, Mr. Kell. Thank you. So in cation exchange, the cations get caught. I don't think I'm going to remember that, girl. I'm sorry. I'm going to try. Cation exchange catches the cations. I kind of like it. It's catchy. So here's the deal. The cations exchange with the negatives and they get held up in here. So they're not going to be the first elutant. They're going to have the longest retention time. So in cation exchange, the elutant first will be the anions. The cations will have the highest retention time because the cation exchange catches the cations. Cation exchange, highest retention time. Now, in anion exchange, so in anion, and they ask this, right? In anion exchange, no, they don't all elute. They don't all elute until you use a salt and break them free. So, yeah, that's kind of another interesting thing, is that in cation exchange, are you trying to isolate anions or cations? And the answer is it could be either. So in cation exchange, you might catch all the cations and then use a salt and break them apart and catch them later and get rid of everything else. You see what I'm saying? At least you know your unknown stuck in the funnel or in the tube. So I guess, so in cation exchange, what are you trying to isolate? The anion or cation? It could be either. Because maybe the anions come off and you catch them. Does that make sense? So no, for sure as hell, if you don't use salt, that stuff's stuck up in your tube. Stick it up your tube. Got it? That makes sense, Ian? Good. Okay, so now in anion exchange, what's in your tube? Sure. What's in your tube in anion exchange? The anion exchange catches the anions. In anion exchange, the tube catches the anions. It's not bad. So you can use it. No, that's still good. In anion exchange, the tube catches the anions. Yeah, it doesn't really work. So negatives are not in here. We're going to catch the anions. Got it? So it has to be positives in the tube. So they'll show you a bunch of different molecules and say which are the most likely to be adhere to the tube in cation exchange or anion exchange. You understand? And pick the ones that's either positive or negative, and pick the one that's more positive because that's better. You see what I'm saying? So they'll be like, oh, would you use Mg plus 2 or would you use sodium plus? Yeah, you want to use Mg plus 2 because it's a bigger positive. It's going to catch the anions better. Okay, so in anion exchange, what's the first elutant? Elutant means you come off. If you guys never heard that word, you should know it. Eluting means it's the thing that comes off. I kind of like that word. In anion exchange, then the negatives are getting caught and the cations are coming off. The first eluting are cations. Cool. They are just super high on anion and cation exchange. It's popped up over this test about a gazillion times. All right, let's do beads. Beads fascinate the hell out of me. I'm not going to lie. I've actually done this and I still am fascinated by it. Like it's kind of ridiculous, but it works. It really works pretty damn well. It's cheap as hell. So here's the premise of bead chromatography. And the bead chromatography is also called size exclusion. So bead chromatography is also called size exclusion chromatography because we're going to exclude based on size. Got it? Bead chromatography. Oh, I was going to say, did I forget? No, I didn't forget. We went over boiling chips. What's an ebulator do? What's an ebulator do? Air. It blows air. For what reason? What's the reason? Surface tension, surface tension. Disrupt your surface tension. Disrupt your surface tension. Got it? Disrupt your surface tension. Good, good, good. For what purpose? Prevent what? Prevent superheating. Prevent superheating. Prevent superheating. Got it? Yeah. Bead chromatography is also called size exclusion. So here's this. This is funny. So you got a big ass protein and you got a little protein, or this works for DNA and RNA too. And what happens is this guy, the little guy's inquisitive, and he goes into all the holes, and he's like, "Oh, what's in here? What's in here?" And big guy has nothing. He doesn't want anything to do with it. He goes right through because he's excluded from going through the holes. But I was just like, well, what if he went through the holes really fast? And it doesn't. I don't know. Whatever. They got to figure it out. That's to me, the kinetics don't make exact sense unless you have. I guess you have enough beads that the little guy's going to go through like every bead. Like, what's preventing a little guy from going around the outside? I don't know, man, but whatever, it works. So you have to understand it. So the bottom line is this. In bead chromatography, the eluting is what? Right or wrong? No, and I know the shit works. I've done it. And I'm like, I never took the time to do the calculations, but I've done this and it works really well. So in the eluting is going to be a big molecule that doesn't fit. Got it? The big molecule doesn't fit. That's all. Now, just because two things elute out, so A and B elute out at the exact same rate, so they have the same retention time. They have 1 second to get the hell out of this thing. Retention time versus eluting is the exact opposite, right? So if they elute out at the same time, can you assume they're the same size? Yes or no? No. All that you know is that you got to adjust your resolution then. And adjust your resolution. Do you need bigger or smaller beads? So they've asked a few questions like that. You need bigger beads. Does everybody understand that? The beads were too little, and then A and B just didn't go through any of them and came right through. They eluted out. Everybody got it? Long story short, I don't know, man. Maybe I'm the only one, but I'm telling you, it always was funny to me. I'm like, what a little curious. Oh my God, look, I'm tiny. I'm curious. What does adjusting the resolution mean? Adjusting resolution means making bigger beads. So now if I have bigger beads, maybe only A can fit and maybe B can't. Got it? The bottom line is that if A and B came out at the same time, could they be the same molecular weight? Yes or no? If A and B, they could be. But all that we know is they have reached they're not big enough to go through any holes, and that's all there is to it. So what do? We adjust the what? No, Rebecca. Could they have both gone through the same holes exactly the same time? Not so much. Got it. So we adjust the resolution. Unlikely, but very unlikely. Almost exceedingly unlikely. I agree. Okay, cool. Happy times. That's bead chromatography. That's definitely one of my favorite. Oh, let's do ELISA. Isn't that like a corny radio show? ELISA. No? That's Delilah. Does increasing bead size help the amount of resolution? No, that is the resolution, dude. And when you change the bead size, that is adjusting the resolution. So when I change the bead size and I use bigger beads or smaller, so it's funny because you basically have, when you do bead chromatography, it's almost like a bead shop, and you have all these different size beads, and you set up all your jars and you run it through, and you keep running it until you separate them better. That's adjusting the resolution. Got it? So, but you always use the same size beads in any given container. You only use one size beads in any given container. Got it? Good. Okay. ELISA is insanely important, and this is enzyme-linked immunoassay. So what does this do? Well, ELISA is kind of cool. So for ELISA, what we do is we we're looking for this protein, let's say, right? So here's a protein. Very expensive and time-consuming test. So really, we only do it as a reflex. We usually don't do it as the first test out of the bat. So in an ELISA, what we do is we get an antibody and we bind the protein of interest. Okay, so we want to find out if you have this protein. So apparently you did, but don't tell anybody yet because we didn't test positive. Well, how do you know this is actually bound? What do? You weigh it? No, you don't weigh it. What do? You run it through an ELISA. An ELISA is a column. So instead of in the column being, instead of the column being beads, there are more antibodies. So this thing can capture the antibody bound to this. You understand? So this antibody, what I didn't tell you, was labeled with a color. So you can zap it with a laser. Got it? Well, it's not an antibody necessarily to the antibody, but it's an antibody to the antibody bound complex. Got it? So now what happens is, as you run it through, we capture the protein and we capture the antibody. Oops, my colors are off here. So we capture the protein and we capture the fluorescence. If it went through, now we zap the laser. Got it? So we zap the laser. And when we zap the laser, it lights up green, red, whatever kind of color we made it. So we hit the laser. So it's an antibody to the antibody complex. And if you bound the antibody complex, it goes. Does the antigen play a role in it? Yeah, dude. The antigen bound to here. That's the whole point. That's why, see, Jewel, this is why your answer wasn't good, because look, dude, what if I just had this antibody floating around, right? So if I had this antibody floating around here, this guy, if it was just an antibody to the antibody, he would capture antibodies and you have a ton of false positives. Does that make sense? Yeah. Nas, you good? Nas. Good. So does the antigen play a role? Yes or no? Hell yeah, it does. It's got to bind to both of them. So this is antigenic. The whole antibody complex is antigenic. Because if it were just an antibody to the antibody, then you'd have false positives everywhere. Get it? So that's one way to do an ELISA. Get it? Got it? Another way is this. They capture the protein. So here's the protein you're looking for, and here's your column. And then they add another antibody that binds to another epitope region, and that's the one that has color. So first, you buy a tube. So you buy the tube with the antibody in it. Got it? The antibody's here. That's how you bought the tube. Then the first thing you do is run the protein. Oh, by the way, between every step you wash to get the stuff out of there, because maybe the protein would just kind of hang around and not be bound. You understand? So you always wash. Don't ever forget that. Between every step, you got to wash everything through, so it's just not chilling out here. So we just washed it. Did you see it went away? So you run the protein. Second thing is you run the antibody with the label, and then third thing you zap it with a laser. So this is another way. So there's a couple ways you can do ELISAs, but the bottom line is this. You've got two antibodies involved, and the antibodies are going to make sure that that protein is there, and you trap it. And that's the deal. I like it. Cool. All right. Beat chromatography. Let's do some NMR. Ooh, yeah, I love NMR. NMR, your John said, man, what are you doing here? Number one in NMR is determine number of signals. This is easy breezy. Determine the number of signals. That's the first thing you're going to do in NMR. Determine number of signals. Number two, you're going to put them on the field. Number three, you are going to analyze each signal. And each signal is the n+1 neighbor rule. And number four, you are going to determine the height of the signal. I got news for you. Number one almost always gets you the answer. Height of the signal is called integration, by the way. And this is the smallest ratio. So if you had 4 hydrogens to 2 hydrogens to 1 hydrogen, that's the smallest ratio. But if you had 6 to 4, the smallest is 3 to 2. Got it? Do I use an iPad for classes? No, I use PCs, but you can use an iPad. Oh, to draw? No, I use an Oogie. You ever hear an oogie? Why is this good or bad, Ian? Are you shitting on my drone, or are you saying it's good? I think it's pretty good. Yeah. Mm. Oh, the speed. Yeah, yeah. No, oogies are awesome. The only thing that sucks, oogies are only like $40, but I go through them like I mean, I probably have about 10 of them because I press too hard, I get excited and end up breaking. So yeah, I have an oogie. This is an oogie. I'm an open book, man. I tell you guys whatever. You guys know what coffee I drink. You guys know what. Oh, hot chocolate, by the way. Land O'Lakes hot chocolate is the best hot chocolate in the world. Land O'Lakes. So anybody who likes hot chocolate, Land O'Lakes, awesome. Culture Cookies is probably gone by now, right? Aw, thanks. Lavaz. All right. So, my little Oogie fans, these are our rules. Number signals, put them on the field, determine each signal, and let's look at the height. Got to memorize. Life 0 to 2 is where methyls appear. Any kind of CH2, CH3s, methyls. They can be shifted by halogens and stuff, but right around 0 to 2 is a good number to know. 4 to 6 are for, what do you call an alkene hydrogens? Land O'Lakes. Land O'Lakes hot chocolate is like heavenly. It's like the most, oh my God. Whew. Land O'Lakes hot chocolate. Something about it. So what is this hydrogen called? That is a vanillic hydrogen. Vanillic means you're an alkene hydrogen. Know it. 6 to 8.5 is what kind of hydrogen? Isn't it aromatic? Don't you think? I think it's a little too aromatic. 9 to 10.5 is a what? Hello, Mr. Cho. Aldehydes. 11 to 12.5 is what? Are they going to give you this in a nice chart like they did in undergrad and basically weren't supposed to because you should have memorized this? This way you wouldn't have to memorize it for me. Was I thinking out loud? So, are they going to give you this chart? Yes or no? Yeah, you're going to have this chart because it's going to be in your freaking brain. That big beluga whale you call a brain right there. Guess what's in there? This chart. Put it in working memory, please. Got it? Sooner rather than later. Good. All right. What's our aromatics? Aromatics. Aromatics. It's the pirate version of aromatics. Aromatics. Got it? Good. Okay. The field. So the field, which side is 0 on? Does anybody remember 0? Which side? It could be on either side. Yeah, different. I love you guys like, no, my machine only. Different NMR machines put the 0 on different sides. Everybody cool? So I'll put the 0 over here. What the hell? Now, don't be confused by the first signal because the first signal has a name. It's called the blank. The first signal, so if you signal a signal at 0, it's not your molecule. It's what's called trimethyl sulfoxide. Yeah, TMS. It's the standard. It's the blank. It's how you calibrate machines, okay? TMS, trimethyl sulfoxide. They actually freaking ask that. That is like a douchey question. Out of all the stuff they can ask, they're really going to ask you what the blanket is in NMR? Trimethyl sulfoxide. Got it? Good. Now, TMS is much more common than carbon tetrachloride. So now, what is it called when you go away from 0? When you go away from 0, we call it downfield, de-shield. Downfield. We don't call it shifting. You don't know if it's a shift. Downfield, de-shield. De-shield, downfield. So going away from 0 is downfield. And the field in proton NMR goes to about 12 or 14. The field for carbon NMR starts here, and carbon NMR goes all the way up in the hundreds. So carbon NMR goes up down here. They don't want you to memorize the carbon NMR numbers, but they do want you to know how it works. So you will know how it works. So downfield, de-shield. De-shield means oxidized. You're losing electrons because you're closest to an electronegative element. And what's the order of electronegative elements? You better know. Funkelverse. Funkelverse. Most electronegatives, fluorine, oxygen, nitrogen, chlorine, bromine, iodine, sulfur. Funkelverse. Who doesn't love a little Funkelverse? No H's. No H's. Okay, now going the other way is up shield. Up field is shielded. Shielded means you are reduced. Means you have a bunch of R groups that push electron density that undergo hyperconjugation. Hyperconjugation just means R groups push. When you have hyperconjugation, it's because sp3s stabilize sp2s. Got it? So a bunch of sp3s pushing. This is called shielding. Groovy. Okie dokie, let's play. So that's our field. We know where things go. We started out very easy breezy. Okay, First things first, how many signals on NMR? How many different types of hydrogens are there? That's what you always do first. One, a two, a three, a four. Does everybody see 4 signals? There are 4 different types of hydrogens in this molecule. You are correct. You are right. 4, 4. 1, 2, 3, 4. Look for symmetry. None of these guys have symmetry with the other ones, so it's not going to be. They're all going to be different. Now, the next step, I believe, was put them on the field. Somewhere between 0 and 2. That might pop a little above 2 because of the chlorine, but who cares? So somewhere around 0 to 2. Which one is the furthest downfield, 1, 2, or 3? Who's the furthest downfield, 1, 2, or 3? 1, absolutely. 1, it's close to electronegative elements. Then 2, then 3, then 4. Got it? Now we're going to do each specific signal. Now we know where they're at. Be honest with you, this is going to get you the answer. There's only going to be one answer with 4 signals, all between 0 and 2. There's only going to be one answer. So click and go. What are you doing right now? Click and go. We should be on the next question. Oh, let's pretend they all had it. Got it? Oh, I forgot to do mass spec too. You got to just remember to do mass spec. Mass spec is really easy. I'll put a note. Mass spec. Click and go. Mass spec. So signal 1. Now we use the n+1 neighbor rule. I go next door. How many hydrogens next door? To my 1, how many hydrogens next door? 2. 2 plus 1 is trips, baby, triplet. Ooh-cha, ooh-cha, ooh-cha. Now, how many hydrogens caused signal 1? 2. So the ratio in height is going to be 2 to 2 to 2 to 3. So 2 hydrogens. Signal 2 is going to be caused by 2. It's going to be the same height as signal 1. How many hydrogens next door? Booyah, booyah. How many hydrogens? A doublet of doublets, a triplet of doublets. You ain't gonna have to know any of that stuff. How many hydrogens next door? We're doing signal 2. I go to 3 and say, hey, how many hydrogens you got in there? Carbon 3 has 2 hydrogens. Carbon 1 has 2 hydrogens. So we got 4. 4 plus 1. Doesn't matter. 4 plus 1 is 5. Look at my beautiful quintet. Quintet. Phrase it like another one. Now, signal 3. How many hydrogens? Notice they're the same height. Scott Roberts. Scott Roberts, they're not exactly the same height. Oh my God, you guys can't. I can't. I just can't, man. Oh man. I gotta save myself an email and draw these things close to the same height, or else I'll get in trouble. Why weren't they same height when you did this? 6-tet. 6, that's sex, baby. Rebecca, that's sex. Sextuplet. 2, so signal 3 has 2 over here. And 1, 2, 3 over here. 3 plus 2 is 5 plus 1 is 6, baby. It's called sextuplet. 1, 2, 3, 4, 5, 6. Oh my God, actually, you're right. Last but not least, bring it home. Baby. Signal 4, I need some room. What is it? Signal 4 gives us a what? Trips, baby, trips. 2 hydrogens, whoops. 2 hydrogens next door, and we get a triplet. I honestly can't believe this was like even a little bit difficult in undergrad, because this is so freaking easy, guys. It really is not that bad. We're going to do a bunch of these, or at least maybe like 3 or 4 more, and you're going to be NMR experts, because this is not terrible. All right, so now let's try another one. Do we need to know coupling? J coupling. Oh my God, doublet of doublets. We are doing coupling, kind of. Got it? The scale's kind of from 0 to about 12 for a proton NMR, and for a carbon NMR, it goes up into the 2 or 300s. Got it? But you don't have to know the carbon, just the protons. Okie dokie. So, Miss Diane, the answer is not really, other than just at this level. You're supposed to be able to pick out an NMR and say what it looks like. So they want you to really know it fast. Get it? Like this. All right, let's do it. How many signals? Show me the signals. By the way, we had some beautiful, beautiful, beautiful. Many of you guys know some of our folks who dropped in January and took the test in January. About 6 or 7 of our students took the test in January, and they just killed it. So that is very, very exciting. Like, people were very happy with the results. I was very happy with most folks' results. Almost all, actually, also all results. Nobody had a bad test. No such thing as bad test, only bad people. All right, here we go. How many signals? I've got one. I've got two. Symmetry, perfect. I've got three. I've got four. Everybody see four things? Yeah, I kind of, yeah, you're fine. Dan, you're going to kill it. I have confidence in me. Here we go. Where are they now? So they got four signals. So we're looking for an answer. So understand, we're looking for an answer with four signals. And what else? What else you want to know? We want four signals. And what? Three of those signals are where? Forget about the heights. Where three of the signals are where? Yeah, we do the regions and get an answer. 12. What? No. 6 to 8.5. No. And where's the other signal? These are simple methyls. So one of the signal is 0 to 2, and then the other guys, the other signals are where? 6 to 8.5. So go get yourself the answer that has one signal between 0 and 2 and three signals between 6 and 8.5, and you got the answer. This is how fast. I mean, folks, they've had like 4 or 5 NMR questions on one freaking test. This is easy stuff once you really know how to do it. So hopefully we're learning. Okay, folks, let's do the methyls first. Do the methyl. Mr. Methyl, Mr. Methyl. How many hydrogens you got next door, Mr. Methyl? Oh, yeah. How many? None. None plus 1. What's none plus 1? None plus 1. Singlet. He's lonely. He's a big one, though. Oh, he's a big one. How tall is he? Oh, she's a nice one. She's 6 tall. Got it? 6. How do you know she's 6? Because there's only a 1. You can't reduce down any further than 1 because signal 1 is going to have only be 1 tall. So signal 1 is going to be tiny. Okay, so now listen. Our groups are not electronegative. They're electropositive. So they don't pull electrons. They push. That is a major premise. Our groups are edges, not EWGAs, electron donating groups. Why 6 hydrogens? 3 and 3. Signal 2 has 6 total hydrogens. Got it? 3 and 3, 6. So our groups are electron donating groups, better known as pushers. And if they're pushers, they're shielders. So who has the most shielding? 1, 3, or 4? 1, 3, or 4? Who has the most shielding? Come on, folks, pay attention. 1, 1, 1, 1, 1, 1. So who's closest to 6? 1, 3, or 4? 1, 1, 1, 1, 1, 1. I love it. I love it. Then we have signal 3. You'd say that signal 4 is the most de-shielded because it's further from the R groups that push electron density and shield things. Wouldn't you say that? Thanks, guys. Okay, so here we go. You ready to go? Signal 1. What do you got, signal 1? Next door, I see 0 plus 1. Say hello to my little singlet tomorrow. Got it? No neighbors. 0. Lonely guy. Signal 3. I see no hydrogens next to me, but oh, I see 1. 1 plus 1. Signal 3 is a nice little doublet. How tall? Twice as tall as 1. 2 hydrogens. 3 and 3. See it now? That's a doublet. Twice as tall. 2 hydrogens. This thing's supposed to be 6 times as tall, but I don't want to draw that high. Okay, I just did. Signal 4. Now, signal 4 is interesting because you get 1 plus 1 plus 2 is triplets, but the triplets overlap. And believe it or not, generally when you have the same hydrogens, it only counts one of them. So this could show up on NMR as a doublet because it's a doublet of doublets, but they overlap with each other because it's the n plus 1 different neighbor rule. Does everybody kind of hear that? So this NMR shit's not perfect. And it depends on how zoomed in you are, but the bottom line is this. If they're the same hydrogen, you generally don't count them, and you only split with one of them because the splits overlap perfectly that you can't even tell, and the machine readout only gives you a doublet. That's what the actual machine gives you, got it? Not some fake textbook example. It's not actually a machine that did it. So you actually get a doublet. How tall is your doublet for signal 4? Because they're the same, 3 and 3 are the same hydrogens. How tall? How tall is your doublet? Tomorrow, it's only a 1 hydrogen tall. I love it. Sweet. Let's play more. Okay, let's do, this is a fun one. Oh, you guys ready to have some real fun? Go for it. NMR in your jar and say, man, what are you doing here? Correct, Miss Olena. You're welcome. So one signal, I love it. Where is it? Between sitting. Yeah, no, Danny, don't fall for that. It's between 4 and 6, sister. That's not aromatic. There's no way in hell that's aromatic. It's vanillic. 4 to 6, baby. All right. You got any neighbors? Hello, I've got a neighbor. I've got a neighbor. I'm a bullywug. Yes, I am. So help me help you. What do you got? Isn't it a doublet? Don't you think? How tall is your doublet? No. How tall is your doublet? No. How tall is your doublet? No. No. Apparently. No. Yay! Carolina in the house. No. Your doublet is 4/4. The machine does not know what the hell a hydrogen is. The machine knows what intensity of signals are. So the machine reads one signal, so it just makes it 1. So how tall? This is going to play a role in the next one, allegedly. So how tall is your signal? 1. Caused by 4 hydrogens, I agree, but it's still only 1 tall. Is that going to be important? We'll see. Boom. Okie dokie, my lovelies. I always wondered if I could use NMR to distinguish between acetone and hexamethyl benzene. Can you use NMR to distinguish these molecules? Of course, right? Sure, of course. I'm not going to do it because I'm lazy. I'm just going to let everything come to me. Everything's handed to me. No, that's not you guys. In the previous example, why would it be a doublet? Boom. Because it has a hydrogen next door. It doesn't matter if you're yourself next door, as long as the neighbors aren't the same neighbors. It's still got a hydrogen next door, so it's 1 hydrogen next door. Hey, I've got a hydrogen next door. Got it? Okie dokie. Oh my goodness. The question was, that's the point. Downfield shifts are only within a molecule. You can't really tell between molecules. That's the whole point, Ian. That's one of the points. But there's going to be a lot more points coming up. Allegedly. Oh, man. This was a good one. This was August from 3 years ago. Allegedly. Yes. Rebecca says yes. One has a benzene rank. That's impressive. So hexamethylbenzene, doesn't that hexamethylbenzene, let's see, that looks like this, right? 1, 2, 3, 4. Yeah, there you go, right? Hexamethyl. No, that's hexobenzene. What the? Who in the what in the? Hexamethylbenzene. Acetone builds up bony. No, it doesn't. Acetone. Now, my lovely troublemakers. Why do I have to do all the work here? Oh, I'm supposed to teach you guys. All right, how many different types of hydrogens in hexamethylbenzene? How many different types of hydrogens? What are they? Come on, today we get. How many different types? One. And they're between 6 and, where are they? Where are the hydrogens? Between what? They're between, yeah, pretty much between 0 and 2 because they're just methyls. Oh. Olena, what's next door, sister? What's next door right there? I see. There's no trick. What's next door? How many hydrogens next door? 0. All right. What do you get for hexamethylbenzene? Between 0 and 2, you get a what? You get a singlet. How tall is your singlet? You've got 18 hydrogens, folks. So how tall is it? It's Naz, where the hell were you? Put down that bologna sandwich. Pay attention. It's 18 over 18. It's always normalized to the lowest number. So how tall is this? It's 1. There is no height. There is no relative. It's really tall. It's really small. There is none. It's just 1 because the heights are integrated and relative to each other. And there's only one type of hydrogen. So the machine doesn't know how to do any other comparison. That's when you say, ow. But now we're going to do what? Acetone, totally different. I mean, this is like ridiculous. Look at this. How many signals are there for these methyls? 1. How tall is it? No, it's not 1. It's 6. Over 6. Rebecca, you know me too well. So, how tall is it? 6 over 6. And what is it? I see no hydrogens, my neighbor. What? So I asked, so the first thing I want you to realize is that there's no, you can't compare this height to this height. You don't run, they haven't made NMR machines that do multiple things at once. You understand what I'm saying? They just haven't. So it's not like they're comparable, the heights in the same sample. You got to, it's only within a sample that the heights are comparable. Not really, Danielle, because you can't really tell what the deshielding from the carbonyl is so minor that you can't really tell. You wouldn't be able to distinguish them. So can you use NMR to distinguish these? Yes. Good. Okay, cool. Let's move on. All right, so can I get a what? 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 Can you use NMR to distinguish acetone, hexamethylbenzene? Yes or no? Yes, 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 yes. Caroline's about to kill me. I better give the answer. What? Scott Roberts? Caroline, you killing me. So, let's try it again. Can you use proton NMR to distinguish these? Yes or no? No. You cannot use proton NMR. But you can use carbon NMR. We're going to talk about that right now. Look at that. Come on, baby. That was a transition into carbon NMR. Come on. So no, not no, but hell no. Thanks, Abby. Thanks. Give me some props there. So you cannot use proton NMR. Got it? But you can use carbon. So let's do it. Don't forget about mass spec. Yeah, I got to hurry up and do mass spec. So thanks, Jake. Keep me honest. So listen, mass spec is quick and easy. You guys are, it's so easy. And they always ask the same damn question. So we'll be there in a minute. So listen, for carbon NMR, how many signals on, so it's the same thing, signals on carbon NMR. So let me step back. You sure as hell can't use proton NMR, folks. They look exactly the same. One might be shifted a little more, but it's so minimal you can't even tell because it's not within the same molecule. That's first thing. Second thing is, carbon NMR tells you how many different carbons, okay? But the height is not relative to the number of carbons anymore. It's a little different. But all I want you to know is how many carbon NMR signals. So acetone gives you 2, a carbonyl signal and a methyl. Hexamethylbenzene gives you a benzene signal and a methyl. Do you think benzene signals and carbonyl signals are in the same place? Yes or no? Of course they're not. You already understand. So the bottom line is both give you 2 signals on carbon NMR, but one gives you a carbonyl versus the benzene signal. And that's how you tell them apart. So yes, you can use NMR and you can use carbon NMR, but no, you cannot use proton NMR because you'll get the same thing. Good. Nailed it. Okay, mass spec. Very quickly. Yes, Rebecca. Mass spec. She's so happy. She has her notes nice and tidy. I love it. So mass spec, long story short, you get molecular weight. And this is awesome for getting molecular weight. Like really awesome for molecular weight. And what it does is in mass spec, they shoot the damn thing with electrons. And they shoot it with electrons and they make cations. They make like carbocations. So you make you split the molecule, you shoot so far, like you just bombard it. And you make all these carbocations. So like I'll make a carbocation here. So let's say I had propane or something, right? I'll make a carbocation here. I'll make a methyl carbocation. I'll make an ethyl carbocation. Like I split everything. You understand? You just keep splitting the molecule with these things. And that's what all these signals are. They're all little carbocations and ions that were formed by splitting it. The most abundant, the tallest one has a name. Okay, so let's step back. First thing, mass spec gets your molecular weight, and it's really good at it. So they're gonna like, why are you doing this? You're gonna get the molecular weight. That's the first thing. The second thing is, how does it do it? It has electron shot, and you create ions, and you do what's called the mass to charge ratio. That's what these things are, MZ ratios. But the charge is almost always 1. So it's really just mass. You understand? So since Z is almost always a +1 because you only shoot it, you'll get lucky and shoot 2, and if you do, it's very little abundant. You won't even see it. So the MZ ends up just being the mass of your particle that you fragment, the mass of your fragment, the mass of your ion. Okay. So there's something called the base peak. And that's not the molecular weight by any stretch. Oh, where's 0? It's the same shit. 0 could be left or right. So over here, I'll do 0 here. This is really, really, really easy. Listen. So this is called the base peak. And the base peak is your most stable carbocation. So in this case, it'd probably be this thing. So that should be downfield a little bit more or whatever. So the base peak is the most stable because it's the most abundant. Got it? The base peak is the most stable fragment and most abundant. But that's okay, and that gets us answers, but it really doesn't mean much, but this means everything. That is the molecular weight. Because whatever happened, like, I don't know, butane or whatever, the carbocation you made stays together at some point. The whole carbocation stays together. And that's going to be, it doesn't have to be, your base peak doesn't have to be the molecular weight. Whatever one's all the way to the left or all the way to the right, away from 0 is your molecular weight. That's it. And that has a name too, of course. What's that called? It's called the molecular ion. So the molecular ion, okay, your M plus is the molecular weight of your substance. So what are all these things? They're all fragments, right? So like, look, if I had this, what kind of fragments would I get? Well, this is my most abundant because it's the most stable. So this, in this case, this fragment, because I lost a hydrogen, right? Remember, I split it. I split a hydrogen off. So you got a hydrogen over here, you split it. So what happened was this, in this case, probably would give me a base peak equal to my molecular weight. So if 0 was over here, I'd see a big ass line up here. But you're also going to get this, and you're also going to get this, and you're also going to get this. It just splits everywhere you can split it, you split it. Get it? So you'll split this thing, you'll shoot it and split it here. So that means you're going to get certainly a propyl fragment. You're certainly going to get an ethyl fragment. Got it? So does everybody understand? So what do I want you to know about mass spec? I want you to know it uses electrons to split the molecule. So in mass spec, it uses electrons to split the molecule. Second thing I want you to know is all those lines are fragments, and they're called MZ ratios. And MZ is just the mass of the fragment. So literally you can tell, oh, look at this fragment. This could be a fragment. And you can add up all your fragments and figure out what the exact molecule is, but that's hard as hell. The biggest thing it tells you is molecular weight. And the molecular weight is going to be the one furthest from 0. That's it. It's the furthest from 0. And then you need to know the base peak is the one that's the tallest. And that's the one that is the most stable ion, usually carbocation. Got it? But I mean, obviously it's nitrogen. It's not a carbocation. And I think that's about, oh, this is really good for one other thing too. It's really good since it's so good at molecular weight. Why is molecular weight furthest from 0? Because it's just the heaviest. Sarah's just the heaviest. Whatever the heaviest fragment is, it means that you only fragmented a hydrogen and you got the whole molecule. Got it? Good. Now, it's really good to distinguish isotopes. Because if it's so good at molecular weight, I can tell which isotope you have. So it's really good at separating isotopes, mass spec. All right, look at that. 801, baby. Woo! Mass spec in 4 minutes. Love it. All right, folks, have a wonderful night. I will see you. I think I see you tomorrow night. What do we do tomorrow night? I don't know if we can schedule. Bio 4. Woohoo! Carolina, peace. Colin, Sammy. What up, Cat? Hey, Scott. Benzene, would there be one doublet signal? Yes. No. Yes. Letitia, what's up? Jake, woo, Letitia, David, Nas, Olena, Rebecca. Rebecca, you always keep it interesting. Shmuel, what's up? Nikhil, you're welcome. No. Factorial. See you tomorrow. Can you please go back to the lysing example? Oh shit. Oh Max. Sure, dude. Just want to see something. And oh God, see, this is when we need Rebecca. Good thing, where was Rebecca to yell at me? Where the hell is lysine, dude? Is that early on? Jesus, it's been a long night. We've done a lot tonight. There's a lot of good stuff. Good night, Miss Sarah. No, don't be sorry, dude. I'll find it. We'll get it eventually. Oh, was that it? Yeah, there you go. Oh, this is, it had to come. I think it did lysine second. Hang on. Ah, there we go. There we go. This one. Cool. Can you clarify again the fraction formula for MR? Oh my God, Danny, are you freaking kidding me? On the NMR, I thought was on the NMR that I thought was an aromatic hydrogen. Can you explain why it's vanillic with the two? Yeah, that's not aromatic, dude. So this is not aromatic because if both these promoted, you'd have 8 electrons and you'd be anti-aromatic. So there's no way in hell it would promote. Got it? Oh. So with the probability of the R group being neutral at pH 7 is 1/10⁴. Would the probability of the R group being neutral be? Yeah, I agree with that. Yes, Max. That's why it's here. Yep. Sure, I'll go to the TLC slide. Max, you good? Oh, nice. Good job. They did test it? That's awesome. I love it. 18/18, you always normalize to the lowest number. So if I said how tall is something with only one type of hydrogens, so how tall in benzene, when you do benzene, how tall is the signal? There's 6 hydrogens, but it's 6 over what? You always normalize to the lowest number. So if I'm 4 to 2, you normalize to 2 and you go 2 to 1. The ratio in heights are 2 to 1. That's all. TLC slide. Oh, look, I labeled TLC. It is really convenient when I label this shit. Rebecca, you've changed my life. I don't know about for the better or worse, but how come with benzene we do N+1, dude, but they're the same hydrogens next door. So we go like this, and we see one hydrogen, and we see one hydrogen, but we went to the same hydrogen. Remember, it's the same hydrogen and overlaps, so it's like a doublet of doublets, but it's really just a doublet. So you're using them, but they're the same hydrogen. Get the idea? So we do it, because we don't get a singlet, we get a doublet. Does that make any sense? Who wanted the TLC? What do you mean? The benzene we did with all the hexamethyls had no aromatic hydrogens. There's no hydrogens on this ring. They're all methyl groups. The 0, 0, 0, 0. Got it? So here's something that tells what benzene would be polar. No, dude, no. This is not polar. B is no what? Elena, no. This is not polar. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is decanone. Decanone is not polar. 6 or more carbons, only one functional group. This is phobic, dude. And that's why it travels. Got it? Elena, are you mixing questions? Are you mixing metaphors again? Yeah. Glad I could be of service. So much fun. You guys are great. All right, guys. Peace. Have a good night. Have a great night, Miss Elena. Always a pleasure. Salt limits is left the build. Booyah.